Let's talk about maximum likelihood estimation. Maximum likelihood estimation, which we often denote or abbreviate by MLE or ML or something like that. So maximum likelihood estimation is a very important technique for estimating a parameter of a distribution. And in some sense, it's maybe the simplest such technique. And oftentimes, so it's very nice because oftentimes it yields sort of the most natural estimates that one might think of. So what is it? So the setup, so the setup for an MLE computation, so to define it, we'll assume that we're given some data. I'll denote by capital D some sequence of points x1 through xn. And so, for example, these might be d-dimensional vectors in d-dimensional real space, or they might be vectors or scalars or something like that. And we assume a family or a set of distributions. Usually we call it a family. Not for any good reason, really. And each of these distributions will denote by p sub theta. And theta ranges over, so theta is the parameter. It could be a vector of parameters. But it's just something that's ranging over a set capital theta, and it indexes these distributions. Oh, and each of these is a distribution on, here it's d-dimensional real space, whatever these x's are taking values in. And we will assume that our data, so we'll assume a model, a probabilistic model for our data. So we will assume that D is a sample from some random variables. So we'll assume that we have some random variables, x1 through xn, distributed according to one of these p thetas, so according to p theta, and their IID for some theta. So we assume that there's some theta in capital theta, that all these points that we observe, so that there are some random variables distributed according to that distribution, and that what we observe is a random draw from these random variables. And now our goal in maximum likelihood estimation is to choose or estimate. We want to find a good value of theta, and ideally, we want to get close to the true value. So we want to estimate the true value of theta that the data comes from. And here comes the definition. So under this sort of setup, with the maximum likelihood estimate is the following, or a maximum likelihood estimate. So a theta, which we'll denote as theta sub MLE, is a maximum likelihood estimate for theta, for the true value, if it satisfies, if it maximizes, so it's equal to, or it's, so I'll write it this way, sort of heuristically, it's equal to the argmax over thetas in the whole range of possible thetas of the probability of the data given theta. So I wrote it this way. This is sort of maybe the natural way to think about it, but a little more precisely, I should say, let me say, more precisely, it maximizes this function. So the probability of the data under theta MLE. Oh, and so I'm sort of I started using this notation instead of our subscript. I'm using so I'm using this sort of alternate way of writing. If I have p sub theta of x for some x in RD, I'm just writing that as p of theta, or p of x given theta. Just another way of writing that. And so, the probability under theta of d would just be this thing, p of d given theta. And this is, since these are IID, this is the product. Maybe I'll write that down below so you can see exactly what I mean. Well, let me finish this and then we'll come back to it. So more precisely, the theta MLE satisfies that the probability of the data under theta MLE equals the maximum value attained for the probability of the data given theta over as theta ranges over all possible thetas. So this is more precisely, or more correctly, the thing, because there might not necessarily be a unique maximizer of this. So there could be more than one. And that's why this is more correct to say. So here, p of d given theta, this is the thing I was about to start writing above. We just mean this, which we could also write as the product, since we're assuming that these are IID. Right, and this is just, probability that xi equals little xi under this distribution. So that's just an aside. So that's the MLE, or that is an MLE, and MLE satisfies this property here. And now a remark, let me make a remark here. I already mentioned the first remark. One is that the MLE and MLE it might not be unique. There could be more than one theta MLE that satisfies this property. Another, somewhat more unsatisfactory remark is that the MLE may fail to exist. There might not be a theta that achieves this maximum. There might not be a theta MLE that has this property. And basically why that can happen is that this function might not have, the maximum might not be achieved at any theta. So I'll give an example of that a little later. Okay, so that's the MLE. This is really the key thing here. And now let's talk about some pros and cons of MLE. So this will just be a little informal sort of discussion of pros or advantages of the MLE and cons or disadvantages. So first, usually the MLE is easy to compute, oftentimes, so that makes it nice to work with. And it's often interpretable. Many times it's, for example, like for the mean of a normal random variable, then it ends up being the sample mean. And so oftentimes it has a very nice sort of intuitive interpretation. Another pro is that well, let me put it over here. It has some nice asymptotic properties. So, for example, I'll just list a few here. It's consistent, and I haven't defined that, but basically that means that as n goes to infinity, as the number of points that you observed goes to infinity, then it converges to the true value of theta with high probability, or with probability 1, actually. So that it's consistent, it's asymptotically consistent, it's asymptotically normal, in the sense that its distribution, when n is very large, its distribution looks normal, and that can be formalized. Converges in distribution to a normal when appropriately rescaled. And it is efficient in the sense that, so it's statistically efficient, asymptotically, in the sense that, and what this means is, without making it formal, is this just means that in some sense it is the best possible estimate of the true theta, in the sense that it has the lowest variance, the lowest asymptotic variance. So its error, without explaining why having a low variance means low error, basically that means that it has low error, the lowest possible error asymptotically of all estimates of this type. Okay, and one last pro here is that it is invariant under reparameterization. And this means that if this means that how do I want to say this? So for any function g of theta MLE is a MLE for g of theta. So if you have your original parameter theta that you're trying to estimate, like the mean of a Gaussian, for example, and you take some function of it, like maybe you square it, and you want the MLE for the square of the mean, then this says that, in fact, you just square the MLE for the mean, and that's your MLE for the square. Now I'd like to mention a few cons. So first, the MLE is a point estimate, so it has no representation of our uncertainty. Ideally, we would look at the posterior distribution on theta given the data, and that would represent how uncertain we are about theta. But the MLE is just a point estimate, so it's just picking some value, and we don't really know whether that's a representative value. And also, it may not be representative of this. So, for example, a particularly bad thing that could happen would be maybe the posterior, or maybe the likelihood function spikes. Oh, by the way, this is called the likelihood function. I should have mentioned that. This is called the likelihood function. And that's why this is called the maximum likelihood estimate, because it's maximizing the likelihood function. And the likelihood function is a function of theta. So that's something which is a bit unusual, usually if it's a function of something that's on the left side. But this is a function of theta, the likelihood function. And okay, I'm running out of time here, so let me stop there, and we'll continue this in another video. So see you soon.